Hello, and welcome to today's presentation on signal simulation and analysis instrument performance considerations when designing advanced driver assistance systems. Today's presenter is Mark Elo, Technical Marketing Manager here at Tequniques. Before we turn it over to Mark, let's review a few housekeeping details. This webcast is being streamed through your computer, so there is no separate dial-in number. For the best audio quality, please make sure your computer speakers or headset are turned on and the volume is adjusted accordingly. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, or if you have difficulty hearing the audio, try pushing the F5 key on your keyboard to refresh the page. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. During the presentation, please type any questions you might have in the Q&A window, and we'll answer as many of those as possible at the end of the webinar. You can also use the Q&A window to let us know of any technical issues you are experiencing during the webinar. You can download a copy of today's slides by clicking on the Resources widget on your screen. In addition, a link to the archived webinar will be sent to you within a few days. So now let's turn it over to Mark Elo.
Thank you. In this presentation, a webinar today, we're going to take a look at some of the instrument performance considerations that you need to take into account when you're designing or verifying advanced driver assist systems based on millimeter wave radar, especially now up in the 76 gigahertz band. I'll start the presentation with a brief introduction to radar, bring in some historical perspective, and talk about why it's so important in automotive radar as one of the primary sensors. Then we'll go on to talk about FMCW, or frequency modulation carrier wave. It's the dominant modulation type used in automotive radar, and we'll explore the difference between traditional radar and an FMCW radar as part of that section. One of the key performance metrics of an FMCW radar is linearity, so we're going to take a look at how we measure linearity and what type of instrumentation we should use for that. And then the second part of the webinar is signal simulation. So I'm going to take a deep look into what to simulate, why we would simulate it, what are targets, what's an atmospheric condition, how do we add noise, what is multipath, what is clutter, and boil that up into a number of requirements that would help you define the instrumentation requirements, whether you're working on a short-range radar in the 76 gigahertz band, or you're working on a long-range radar. So let's take a look at radar and get everybody up to the same level. So why is it a useful sensor? What kind of measurements can a radar do with respect to an automotive sensing system? What type of radars are there out there? Where do they come from? How have they evolved over time from simple pulse radars to the FMCW radars that we have today? As a radar guy, I'm going to tell you why radar is better than all the other sensors. But ultimately, for a vehicle and a driver to get a full picture of the situational awareness, you need multiple sensors that perform different roles. And we call that sometimes sensor fusion, where a bunch of sensors are going to go out, analyze the environment, and then draw a picture for the driver on what the situation is around the vehicle. As part of the situational awareness picture, radar does give you some key metrics. Distance or range, that's the original use for radar. In fact, radar stands for radio detection and ranging. Speed, we can look at and compare the transmitted frequency to the received frequency, and through the Doppler effect determine the speed. Direction and situation with respect to other objects can all be derived by using multiple antennas, multiple receive antennas usually in automotive applications, but you can also create wavefronts on the transmitter and transmit a beam in a certain direction if required as well with radar. I think depending what country you come from, everybody has a different story of who invented radar or where did radar come from. Many go back to when Heinrich Hertz figured out or discovered that if you point some electromagnetic energy at a metal object, you get a reflection back. As a British guy, of course, I always look to Watson Watt, who was responding to an RFI, a request for information from the British government, who wanted to build an invisible death ray. There was a £1,000 prize if you could kill a sheep at 100 paces. And later on in the presentation, we will look at the radar range equation and all agree that that's quite difficult. But what he did manage to do was to convince the British government that he could spot aircraft using radio waves that were beyond the line of sight, and give the country a little more advanced warning of an invading force. And eventually the British government decided to give him some money to do his research, and the rest is history. So radar fundamentals. So what are we going to do here? We're going to take a pulse of radio energy. We're going to emit it from an antenna. It will travel at the speed of light towards an object, and then it will reflect back off that object. The difference in time it takes that pulse of energy to bounce off the object and return is equivalent to the distance. And as the radio waves is going at the speed of light, it's actually that the distance is equal to the time it takes the signal to bounce off the object and come back times the speed of light, and then you divide it by 2 because of course it's a round trip and we're only interested in the time it takes the signal to bounce back. Then, as I mentioned in one of the earlier slides, that pulse of RF radiation has a frequency, and when that is reflected off a moving object, the frequency will change, only by a small amount, but the movement in the object it reflects off creates what's called the Doppler effect, and then so we have a difference in frequency. So the velocity is equal to the return Doppler frequency over the transmit frequency, all times by the speed of light and divided by 2 for the round trip return. The next thing to consider in our 3 primary radar equations is the power. So we transmit some RF energy, it travels through the ether, it bounces off the object and returns. And really that is a very important factor, because the transmit power really defines what is the most distant object that you can spot with your radar. So the power has to be of a high enough amplitude that you do get the return signal, so you can measure the Doppler and the distance. So that's what we call the radar range equation there at the bottom, and it's primarily a function of distance. Of course, when you bounce a pulse off an object, like I just explained in the last slide, there's many ambiguities, there's many things that could happen, there's many situations where it's not as simple. You might get 2 returns instead of 1 return, you might miss a return, but what I'd really like to focus on, because it's quite important when we try and understand automotive radar, and especially FMCW, is range resolution. So if we have 2 targets together, and we transmit a wide pulse of energy, the likelihood of the 2 targets, it's discriminating that there's 2 targets is pretty low. So to get to the level where you can spot the 2 targets, you really need a narrow pulse width. The problem with a narrow pulse width is it's very hard to amplify. The gain bandwidth product of an amplifier usually means that you know a really high performing amplifier to be able to transmit a very narrow pulse over a long distance. So this was always one of the deficiencies of pulsed radar in the past, and also it is a factor of why a lot of cost, which is not so good for the automotive market, would be added to a radar as well. So I'm going to talk a little bit more about that in the next slide and how we overcome that. Just after the Second World War, a gentleman called Sidney Darlington at Bell Labs proposed the pulse compression technique, or what we call linear frequency modulation, or what we would call a chirp, as a way to get good range resolution but still have a long pulse. Coincidentally, Sidney Darlington also invented the Darlington pair, which is used in many amplifier applications. Back on topic though, an LFM, a linear frequency modulation, or a chirp is a long duration pulse. And in this example here, I've actually split the long duration pulse into 4 discrete frequencies: F1, F2, F3, and F4. And at the bottom of the slide, you can see we have the receiver block diagram. So we're transmitting the top part, and we're receiving these 4 frequencies. We're filtering each one of those frequencies and then delaying and summing them. And what we get is the equivalent in the receiver chain of the electromagnetic energy summed, all arriving at the same time at the measurement circuit, and giving us a good representation of a narrow pulse, and that is what we need to be able to discriminate multiple targets that are very close together. So this is key, linear frequency modulation, called a chirp, of course, because you know, if you would listen to it, and many electronic warfare officers would listen to chirps during the Cold War, because you could identify the threat, the radar that's tracking you and ultimately connected to the missile system that's going to shoot you down. You could identify that by listening to the sound of the frequency modulation, and it would sound like a bird chirping. So we've learned a few things in the last couple of slides. All around pulse radar, we can transmit a pulse of energy. It reflects off a target. The width of the pulse is going to determine if you can discriminate between multiple targets that are close together. The frequency of the returned pulse and how that differs from the transmit frequency. I'll tell you what the Doppler is. If the pulse becomes too narrow, you need a very elaborate amplification scheme, or you change the modulation type to linear frequency modulation or a chirp, and then that will allow you to retransmit a large pulse, but the way you receive it and process it with some tuned filters allows you to get back to a narrow pulse. Pulse radar is good at measuring range and measuring velocity, and it doesn't take too much processing. Everything that we've looked at today is pretty easy to understand, and pretty easy for a measurement system to determine range and velocity. It's got good long range, especially if you use linear frequency modulation. It's not so good at short range, of course, because you've got to deal with different pulse repetition intervals to determine if it's different pulse widths. And so if you've got a narrow pulse with a small pulse repetition interval, you're not going to be able to see faraway targets, or the faraway targets will look like multiple returns. And one of the key things about pulse radar, it's very good in aviation applications, it's very good in military applications, but there is a high cost associated with transmitting the pulse and the amplifier involved with that. A lower cost approach to get range and velocity information from a target would be to use FMCW, and so this is the dominant modulation type today. There's variants on it, of course, but the dominant modulation type for automotive applications is FMCW. So let's take a look at how that differs from the pulse modulation examples I just gave. So this is an FMCW radar in its most simplest form. I've put a static target here on the right hand side, and we've got a transmitter and receiver. So when you take a look at the transmit and receive in terms of what does that block diagram look like, that's what I'm showing on the left hand side of the slide. So essentially we're sweeping a frequency. So we've got a VCO, so we put a voltage ramp into VCO and it creates a frequency sweep proportional to that voltage ramp, and we transmit that through the circulator. There is a coupler in the transmit path, so what we do is we sniff off parts of our transmit signal from the coupler, and we also take the receive signal out of the circulator and put it through a mixer. And so what that allows us to see is the difference in the difference in the two frequencies, which we then put into some processing and decision-making system. If we look at the sawtooth diagrams on the right-hand side, this explains it a little more clearly. So I've changed the vertical axis now on the graphs. In all the other graphs that we showed, the vertical axis was amplitude. Now it's frequency. So we're sweeping a frequency through the center frequency, and then we're sweeping it again, and we reset, and then we sweep again. So that's what we transmit. We hit our static target, and it bounces back. And the time difference, again, between those two frequency sweeps equals the distance or the distance or the range of the target. When we transmitted the pulse, we had a defined start time, i.e. the start of the pulse transmission, and then we could simply compare that to the receive time. With FMCW, it's not as easy to compare those times because we're dealing with frequency ramps. But we can do a little bit of mathematics, and you know, if on the upper equation there we have tau over the time of the coherent pulse interval. That is actually from the pulse modulated radar, and that is equivalent to the transmit frequency minus the receive frequency over the bandwidth, i.e. the frequency bandwidth of the chirp. You know, if it's like a 600 megahertz chirp, that's the bandwidth. If it's a 4 gigahertz chirp, that's the bandwidth. So we can use that as an assumption, and then we can roll all that back into the radar distance equations, and what we end up with is the distance is equal to the frequency of transmission minus the frequency of receive over the bandwidth multiplied by the time of the coherent pulse interval, i.e. the length of the chirp, times wave speed of light, and divided by 2, of course, because we're looking at a round trip. And this is great, but it's only good, and this is why I put in the example that we have a static target. It's only good if the target is not moving. If the target is moving, then we have to consider a few more things. What's very hard to pull out of the previous example is the Doppler. So what we do is, to get the Doppler, we make two measurements. So essentially, you know, if I skipped over all the math at the bottom of the page, we have two simultaneous equations, one from the up chirp and the other from what we call the down chirp. So we get the two measurements, and then we can extract the Doppler out of that. So now we've got range and Doppler, so we can determine the distance and the speed of the target. But now I put a little note at the bottom of the slide saying, but this is for only single targets. So a single target range and velocity. What happens if there's multiple targets? Well, let's look at that on the next slide. So if we just use the up chirp and the down chirp measurements that we talked about in the previous slide, if there was more than two targets, if there was two targets, for example, we would actually get 4 returns. And so 2 are real and 2 are not real. And to be able to figure out which 2 are the real ones, we usually plot that on a velocity versus range graph, and then we add another chirp. And now the difference between this chirp, the up and down chirp, is going at the same frequency rate, and the third chirp we add is going at a different frequency rate, as you can see in the diagram. And this gives us enough new information to be able to detect or figure out mathematically which two returns are the real returns and which two returns are the false returns. I spent a lot of time so far on chirp modulation, all the way from the history of the chirp and to all the way up until how you would discriminate two targets using different chirp sequences. And I've gone through that because it's the linearity of the chirp that really gives us an accurate measurement. So if we're trying to work out range and we need a good range resolution, yeah, sure, you need a very long chirp to do that, or a very wide bandwidth chirp, I should say. But if that chirp isn't linear, i.e. if it doesn't sweep in a linear manner, you're going to have, and I can show you on the diagram right there in the center, so if we zoom in to what looks like a linear chirp, in reality, because at the end of the day, an automotive radar will be optimized for cost, so it won't be like a military radar. And it will use some basic components, and there will be some compromises, and the chirp may be not so linear. And what we need to do is verify how linear the chirp is, because it's fundamental to understanding our target's range and velocity. And usually we do that using a broadband time domain capture device, such as an oscilloscope. We downconvert it from, say, 76 or 74 or 80 gigahertz, using a standard down converter with a local oscillator. We get an IF frequency, say, of around 5 gigs. We put that into the scope, we do the FMCW modulation, and then we measure the linearity of the chirp. And we can measure the linearity of the chirp not only in how linear it is, but what's the frequency response of the received signal, and again, what's the phase response of the received signal as well. All key measurements for understanding the performance of your transmitter. And when choosing your broadband acquisition device or oscilloscope, it's important to understand the performance of the instrument. So say our down converter gives us a 5 gig signal and we want to look at our down converter gives us a 5 gigs IF and we want to look at a 4 gigahertz chirp. So that's going to sweep from 3 gigs to 7 gigs. So we want to make sure that the instrument has enough frequency range to do that. So I picked two Tequniques oscilloscopes here, one a mid-performance, the 6 series, the new 6 series MSO, and a high-performance DPO 70,000 oscilloscope. So one of them has 8 gigahertz of bandwidth. It's got 12 bits of resolution, so you get a very good amplitude resolution with the 12 bits. With the 8 gigs of bandwidth, we can also comfortably center up at 5 gigs as the IF and sweep between 2 gigs and 7 gigs and be in a reasonably flat region of the oscilloscope. If it was a larger chirp than 4 gigs, maybe we have to use a higher frequency oscilloscope, such as DPO 70,000. That samples at 50 gigasamples per second. Or 100 gigasamples per second, depending on what options you buy, as opposed to the 12 gigahertz. But the resolution of the ADC now is a little less, and so you won't see as many amplitude increments as you would with the 12-bit. And predominantly, as we're working with an FM signal, that might not be as important. But it's really important to figure that you've got the right bandwidth of oscilloscope, and you're going to measure a number of power ranges as well. So the resolution of your A to D converter is of reasonable importance as well. We also need to consider the performance of the down converter as well. So your Tequniques application engineer is going to help you choose the right down converter for the application that you're looking at. And it's a function of where you want to place your center frequency as opposed to the instrument that you're going to use to analyze it. It's a function of the width of the chirp. You don't want to, say, have a large harmonic you've got a 4 gigahertz chirp. You're moving from 3 gigs to 7 gigs, and so if you've got a very large harmonic in that system, when you're at 3 gigs, you're going to get a harmonic at 6 gigs. So these are some things to take into consideration when you're trying to do a measurement of this type. And also, it's handy or useful, you know, with the scope with its 12 bits of range. If you want to look at the spectrum, I'd probably advise that you use a true spectrum analyzer, such as one of Tequniques' USB spectrum analyzers, because it has a much better dynamic range than an oscilloscope. So if you're looking at power, intermods, or spares, spectrum analyzers are a key tool to do that. Depending on how you do your sensor fusion, you're going to connect up a bunch of sensors, either as independent self-contained sensors or sensors that don't really do anything, that send large amounts of data back to a central ECU. But they're all going to sit on some kind of bus within an in-vehicle network. And sometimes you probably need your wideband acquisition device, such as the oscilloscope, to not only be able to measure the chirp and the transmission characteristics of the chirp, but it's also useful that that scope can double up and sit on the bus and actually do some control. So let's take a look at this next. An oscilloscope such as the 5 or 6 series MSO from Tequniques actually has protocol DECODE, and it can look at multiple buses simultaneously as well. And we could use that probably to trigger RF measurements. So we send a command out to an ECU, and we're monitoring the packets on that bus, and we know that we're going to transmit a sequence of pulses, or we're going to activate something in the radar, or we're about to receive something, and we can use that to control external instrumentation. So let's take a look at here. In this example, you can see that we actually have the radar module sat on the bus of the vehicle, and we have the oscilloscope attached to the bus. And what we're doing is decoding the CAN FD bus, and we've set the oscilloscope to send a trigger on a specific message within that serial transmission, and when it receives that serial message, it'll send an event trigger to the spectrum analyzer to make a measurement. That event trigger could also go to another oscilloscope if we chose to, if we want to measure long pulse sequences or determine the value of chirps, determine the quality of chirps at specific instances in time. It doesn't have to be a receiver either. You could use this to trigger an arbitrary waveform generator. So you tell the radar module to transmit, so the appropriate words are sat in the serial packets, and then we trigger a return using an arbitrary waveform generator. So arbitrary waveform generators, the heart of signal simulation. So let's take a look at what does signal simulation mean in terms of automotive radar, and what's the best way to create an electromagnetic environment. So here are the 2 common frequency ranges. So the lower one, the 24 gigahertz band, wavelength of about 12 millimeters, we'd see chirp durations of about 200 megahertz, and predominantly used for short-range radar. And of course, a short-range radar needs very long chirps, so the actual resolution of a 200 megahertz chirp is considerably smaller than that of say a 4 gigahertz linear frequency modulation, which you see more of in the newer frequency band on the right-hand side of the slide, where we're getting chirps between 600 megs and 4 gigahertz. Some are used for long-range radar, especially 600 megahertz and below, and then the wider chirps, such as a 4 gigahertz, are used for short-range radar, where resolution is very important. And if you know your physics, you know that the frequency and wavelength are related. So the wavelength up in the higher frequency bands, 77, 81, 76, are about 4 millimeters. And so that means the devices can be a lot smaller. You can embed them behind the grille of the car, if the car's still got a grille, and they're reasonably small devices. Plus, regulation for maximum power is much higher in these newer bands as well, so you can get a longer range with the radar as well. So all indications are that the higher frequency band, around 76 gigahertz band, is going to be the dominant band for radar as we go forward, and we'll see new products in the 24 gigahertz. We won't see so many new products in the 24 gigahertz band. So I've talked about wavelength. And so one thing that we have to consider in high-frequency transmissions is that eventually you'll hit a wavelength that is equal or proportional or close to or divisible by a molecule of oxygen or some water vapor or some other gaseous constituent in the atmosphere. And these losses can be high at certain frequencies, and a little lower at other frequencies. So I put a green and a blue line in this graph to show where the two bands lie. So you get less atmospheric attenuation in the lower band and a bit more in the higher band, but in general I think it's negligible. But if we're doing some short-range stuff, or we want to get the maximum range out of our radar, we do have to take atmospheric conditions into account when we're testing the limits of the devices that we want to verify are safe for our customers. Next consideration is the antenna pattern itself. Are we creating an accurate representation of the antenna pattern that we transmitted? So an antenna pattern is usually and I used a horn antenna here, and an approximation to a horn antenna's antenna pattern. So we have a main beam, and then we have a number of side lobes. Sometimes you have back lobes as well. And what we want to make sure when you're designing the antenna system, you want to make sure the lobes are as low as you possibly can make it within the cost constraints of the design. The higher the lobes are, the more incidences of clutter you're going to get. So that's one thing to consider. But also, when you're in a high clutter environment, you probably want to be able to have a good representation of your antenna pattern to be able to verify that you're measuring real signals, or you're IDing real signals versus false signals. Next thing to consider, radar cross-section. All cars are not created equal. A lot of cars actually have more plastic or composite materials in than they have metal, and radar loves metal. Radar's not so good at plastic. So if you look at our radar range equation here, you'll see that I've bolded the radar cross-section component of that. So it does have a reasonable effect on the range and the signal that's returned. And part of any qualification of any radar system, be it a military system or an automotive system, is to be able to test the radar under a number of different target scenarios or vehicles with different radar cross sections. So this is another important thing that we need to blend into our signal simulation model that we're going to build in our arbitrary waveform generator. So if I had to define the signal simulation requirements for an instrument, one, you need the appropriate signal generation software, and most test and measurement companies have very good signal generation software, as does Tequniques. Frequency range, of course, we need to get up to 81 gigahertz. We talked about the spectrum allocations. We need to be able to generate bandwidth up to 4 gigahertz or even more, as we see the requirement for resolution get more and more. You need the dynamic range, as I've talked about. You need to simulate antenna patterns, radar cross sections. You need to be able to, have enough range to put multiple targets and to be able to classify them in terms of distance and amplitudes. You've got to have the frequency linearity, and arbitrary waveform generator, being a digital processing device, has excellent linearity, unlike sweeping a basic voltage-controlled oscillator. Phase noise, not so much. It affects Doppler, but more impulse radars. If you look at the 2 beat frequencies of the transmit versus the receive that I talked about earlier in those two frequency sweeps. That's a much higher frequency than the Doppler, but it is good to be able to hook up multiple arbitrary waveform generators and emulate different angles, and perform different angle of arrival measurements. So this is my view of the world when we talk about arbitrary waveform generators. We need to generate the radar cross-section. Is it a car, truck, bike or bridge? Street sign. We've got a number of velocity cases that we need to emulate. Rapid delta in velocity decrease or increase. Susceptibility. There'll be other radars in this environment. It's going to be a congested environment as we go forward. Range cases, of course, with ambiguity, targets close together or are they far away? Are the multiple targets gathered in a cluster? Can we detect each one of those targets and identify them? Atmospheric, I talked about rain and fog are key measurements in the industry right now to verify the radar is functioning correctly. And then clutter. Usually caused by high antenna lobes, but we've got curves, we've got signs, we've got manhole covers, we've got piping going over bridges, all things that could be classified as clutter or could be legitimate targets as well. A curve in a short-range radar is a legitimate target, for example. Tequniques have a product called SourceExpress, and that's the software that we use to generate all these scenarios. So we have all the modulation types, the up and down chirps that we need to generate. We can simulate antenna scan patterns, we can do different beam profiles, we can do the radio cross-section for different target returns, and the different Doppler frequencies. So the software works on both types of hardware. So we have high-performance arbitrary waveform generators and mid-performance arbitrary generators. Some are good for target generation of long-range targets, and others are great for generation of short-range targets. Here's a basic example of me generating an arbitrary waveform of an up and down chirp, which you can see in the lower right-hand side of the screen. I've centered it up at 2.5 gigahertz, and I'll be passing that to an up converter. So reasonably intuitive and simple user interface. So we have our up and down chirp that I showed you in the last example. So here I'm adding an antenna pattern. I'm adding some noise distortion, and I'm also adding some group delay effects to the signal to make sure that we can stress our radar or vehicle under test to really be able to pick out some of the corner cases that could cause a fatal error in the performance of the vehicle. So you did hear me talk about the hardware briefly a few slides ago. This is the AWG 5200. This is an 8-channel arbitrary waveform generator, so excellent for high fidelity multi-channel target generation. It's very good for long range radar. A radar that has a chirp of probably less than a gigahertz. And so this would be a good tool for generating 600 megs, 500 megs, 800 megs chirps on each one of its 8 channels to emulate different targets. It also has a numerically controlled oscillator and an IQ modulator built into the silicon of the instrument. And so we can center these chirps up at different center frequencies without using too much waveform memory. So a good long-range radar simulation, multi-target simulation device. For short-range radar, we need better range resolution because the targets are, potentially are going to be less than a meter away. So we need very large chirps, 4 gigahertz, 3 gigahertz, maybe even 6 as we go forward. So we need an arbitrary waveform generator, with a sample rate of, say, 50 gigasamples like the AWG 70,000 that can allow us, within the first Nyquist range of the instrument to generate a center frequency with a wide with a wide frequency bandwidth, and you can see on the diagram there I suggested a center frequency for a specific wideband LFM that we can then connect to the up converter and ultimately transmit to the receiver under test. So to conclude, to me it's about fidelity in terms of signal generation, and it's about linearity in terms of signal verification of the transmitter. In terms of signal generation, fidelity is all about having the right dynamic range in your ADCs, having the linearity and AWG offers, being able to have multiple instruments phase coherently locked together to emulate short-range radar or long-range radar. So on the left-hand side there, you can see a stack of high-performance arbitrary waveform generators that allow us to create these very linear, very accurate, high-fidelity, multi-target, short-range radar returns. And then slightly to the right of that, we've got the 8-channel high-density arbitrary waveform generator, again, very good linearity, which is good for long-range radar, and we can add our distortions to this for noise, multipath, antenna patterns, etc., as we talked about. And signal quality, we're going to take a down converter and put it into a wideband acquisition device, different scopes with different sampling rates. The MSL6 series with its 8 gigahertz of bandwidth and very high wide dynamic range is a great product. If we want higher levels of fidelity, then we would move to a higher sample oscilloscope, such as a 70,000 oscilloscope. If we want to do good frequency domain measurements, I recommend that a spectrum analyzer is always the best tool for that. And Tequniques have a range of high dynamic range, high performance real-time spectrum analyzers. And with that, I'll conclude. And thank you all for joining, and I'll address some of the questions that came in during the presentation. And of course, please feel free to type in any more questions that you have in this Q&A session. Thank you. I'm not sure if we have an audio problem. Can anybody hear me? Oh, great. So I think I only saw one question come in if anybody's there, and I answered it earlier, but it seems that it didn't come through. But one question was, why can't you use a spectrum analyzer? And the answer is a spectrum analyzer to measure a chirp. And the answer is that they have very narrow bandwidth usually compared to the chirp with a 600 megahertz or up to a 4 gigahertz chirp. So it's not a very good instrument for measuring chirps, but good for measuring spectrum such as spurious. So I didn't see any other questions come in, so I'm going to wrap up. Thank you all for attending today, and we'll send the slides out. And if you have any questions, please follow up, and we'd be happy to talk to you some more about instrumentation needs for ADAS testing. Thank you. Have a good day.